Hello everyone. In this video we are going to study the electric force and how do charge and distance affect electric force. For this we are going to use this simulation here. We have two charges, two spheres. So far they have no charge. Now I can change the charge by this slider here. If I move this to the left, I give it a negative charge. If I move it to the right, I give it a positive charge. The same for this, negative, positive. Okay. Also here I have the distance. I can control the distance as well. But when I change the charge, I keep the distance constant, and this is by turning this button off. Okay. This charge 1 and charge 2 are on. See here. This means that I'm controlling the charge to study the effect of the charge on the force. Then, after that, I turn the charge off and change the distance to see the effect of the distance on the electric force. Alright? And every time I'm studying a variable, we see here a graph for F for the variation of the force as function of the charge. And on the second time, when I'm studying the distance, we see the variation of the force as function of separation or distance or meters. Alright? Okay, so let's start here by keeping the distance constant or fixed and changing charges Q1 and Q2. I'll name this Q1 and this one Q2. Now the separation between Q1 and Q2 is 0.10 meters. And I will give this a charge of +2 and this is -1. Now the force between them is attractive. You see the arrows are pointing toward each other, but of course in opposite direction. And the force between them is 1.80 Newton. So Q1 exerts a force of 1.80 Newton on Q2, and Q2 exerts the same force on Q1, equal in magnitudes but opposite in direction. This is the action-reaction principle, which is the Newton's third law. Alright, so I start with Q12 and Q2 -1. Again, we are studying the variation or the effect of the product of Q1 Q2 on force. Now the product of Q1 and the Q2 here, it's 2 times -1. And if we take the absolute value of -1, then it's +1 times 2, it's 2. So the product of Q1 and Q2 is 2. The force is 1.80 Newton. Now, if Q1 and Q2, if the product Q1 Q2 is doubled, then we will see how will the force be affected. So Q1 Q2 is 2 here. To make it 4 double يعني, I make this one -2. Okay, so F1 is equal to 1.80 Newton when Q1 and Q2 is 2, the product is 2. F2, now it's 3.6, 60 Newton when the product is 4. Okay, so here I have twice double. You see here F2 is also twice F1. 3.6 is 2 times 1.8, so also times 2. Okay, if we make the product 6, make this 3. I make this +3. Now the product is 6. Alright? So the product is 6. Now F3 is 5.39 newtons. So from 2 to 6, it's times 3. 1.80 times 3 also will give 5.39. Actually, it's 5.40. 1.8 times 3. Yes, 5.4. And here I have 5.39. Approximately is 5.4. So as you see here, as the product of Q1 and Q2 increases, the force also increases at the same rate. If this is doubled, the force is doubled. If this is tripled, force is tripled. This relationship is shown here as a straight line, and straight line passing through the origin. As we said, because it's a linear relationship. Okay, so all linear relationships have or appear as a straight line passing through the origin. Okay, so this is for the effect of the charge on the electric force. Okay, so now let's study the distance, how the distance affects the electric force. Type. So let's keep the charge as 3 and minus 2. Okay, and now I will change the distance. At a distance of 0.10 meters, the force is 5.39. Let me record this. So F is equal to 5.39 when R is 0.10 meters. Okay? Now if I increase the distance, let's see now the effect of the force, I mean the effect of the distance if I double the effect of the distance on the force when I double the distance. Yeah, I make the distance 2 times larger. Now they are 0.2 meters apart. Now the force is 1.35. Okay, so F now is 1.35 when the distance is 0.20 meters. The distance now is doubled. Here I have times 2. Now, is the force also doubled? As you see here that the force is reduced. So the first point here we conclude is that the force decreases. When the distance increases, the force decreases. And by what factor? It's obvious here that it's not divided by 2. No, it's divided by the square of 2, by 4. So from here to here, it's divided by 4. 5.39 divided by 4, it's 1.3475, approximately 1.35. Why 4? Because 4 is the square of 2. Okay? If I make the distance 3 times larger, now the force is 0.60 Newton. F is 0.60 Newton when R is 0.30 meters. From here to here now I have times 3. From here to here it's divided by the square of 3, which is divided by 9. 5.39 divided by 9 equal 0.598, approximately 0.6. So we can say here that the force is inversely proportional to the square of the distance. Okay? Inversely proportional because the force is decreasing when we increase the distance, and to the square. If the distance is doubled, then the force is reduced 4 times, by 4 times. If the distance is 3 times larger, the force is 9 times less or lower. Okay? This sort of relationship is shown here. This is an inverse square inverse relationship. All square inverse relationships have this kind of graph. Okay? The further we separate the charges, the less the force. See here, it's approaching zero. The farther the charges are, the weaker the force of attraction or the electric force between them. Okay? I hope this is gives you a clear idea about the variables which affect the force. Again, they are the product of Q1 and Q2. As Q1 and Q2 increase, the force also increases at the same rate. And the second variable or the second factor is the distance. As the distance increases, the force decreases. And it's an inverse square relationship. If the distance is doubled, this means that the force is reduced by 4 times. Okay? Thank you so much, and bye-bye.